For the last talk, we have Caroline from York University, and she's a master's student that works with Dr. Falla. She's going to talk about the effect of distractors and saccade trajectories. Her title is Spatial Profile of Distractors Modifies Saccades Trajectories. Thank you, Caroline, for your talk, and we are looking to hear your talk. Thanks.
Almost forgot to unmute myself. Okay, thanks for the introduction. Oops. Sorry, having a bit of an issue here. There we go. All right. When you're making a saccadic eye movement from a central fixation cross to a target object, such as this red circle here, if the target is the only thing on the display, the saccade you make will be relatively straight towards the target, and it'll follow the direct path. Whereas when there are multiple objects on the display, such as a target object and a distractor object, like this blue circle, both objects will compete for your attention according to previous research, and you'll end up with a saccade that initially angles itself at the average of the two object locations, and then it'll curve to compensate as it goes to the target. And this curvature towards the distractor object is seen for short saccadic reaction times, or SRTs, which reflects the distractor's ability to capture gaze. For longer reaction times, we're able to fully cortically process both objects and inhibit the distractor, and so we end up with a curvature that points away from the distractor. Previous studies that have investigated the distractor's effect on saccades have kept the distractor at a set distance to the target, as well as keeping it very similar to the target. So to better understand the target-distractor interaction, we varied the distance of the distractor to the target, as well as the similarity. And so when there's enough time for this cortical inhibition of the distractor at these long reaction times, we expect that as angular distance changes, saccade curvature will vary according to this spatial suppressive surround annulus. And so this is the idea that when the target and distractor are close enough together, they're in an attentional or excitatory spotlight, but as the distractor moves further away, it is suppressed according to this gradient, where we get the most suppression at a medium distance away from the target. And as the distractor moves even further, we get suppression that's reduced. And since a suppressive surround has also been found in feature space for simple features like color and direction of motion, we expect that there could be a complex object space suppressive surround, which we hope would see a similar modulation of curvature when we vary the similarity between the target and distractor. Participants were first shown a preview of the target, and then were later asked to fixate on the central fixation cross, use their peripheral vision to figure out which object is the target, and then make a saccade to the target. And we varied the distance by what we called angular distance in an egocentric reference frame. And the target could be placed at any of these positions around the display, but for today's discussion, we'll just use the top location. And the distractor would then be placed relative to the target at one of these 10 positions, either on the clockwise or counterclockwise side. We also varied the similarity between the objects, and these are examples of the novel complex stimuli we used, from which we were able to create objective similarity differences. So similarity difference 1 would mean there is 1 line difference between the stimuli, and 2 would mean there are 2 line differences. We went up to 4 for this study, and so just keep in mind that a higher similarity difference means that the objects are less similar to each other. And in another study, we found that perceptual similarity also follows this objective similarity. We used a variety of metrics to measure the saccade trajectory, such as initial angle, which is taking the 20% point along the length of the saccade, and the angle between that and the direct path. And then the sum curvature, which is taking all the deviations away from the direct path and adding them all up. We split our results by saccade reaction time due to the differences in curvature we saw earlier. So looking at short reaction times, we see that as angular distance increases, the initial angle decreases, whereas sum curvature increases and then plateaus around angular distance 3. Both these effects are significant, and it's indicative of not having enough time to inhibit the distractor. And so we get that the saccade angles itself at the average of the object locations, and then curves when both objects are far enough away from each other to cause competition for your attention. And we see a different effect for long reaction times. We get this U-shaped curve for both initial angle and some curvature, which supports the idea of the spatial suppressive surround. So at angular distance 3, we see the most curvature away from the distractor because we get the most suppression of the distractor. For similarity, as expected for short reaction times, we don't see any effects on the curvature. But for long, we see an effect on initial angle only, whereas the objects become less similar to each other, the saccade is initially angling more away from the distractor. And in conclusion, angular distance affects the saccade curvature and initial angle for both short and long reaction times, but it's at these long reaction times when we find this pattern of inhibition that supports the spatial suppressive surround because we're able to cortically process both objects. Whereas for similarity, we only see this affecting the initial angle for long reaction times, which suggests that more complex objects do not have an object space suppressive surround like the simple features do. And what we did see is that the less similar the objects get, we're able to inhibit the distractor more. So with that, I'd like to say thanks, and thanks for listening.
Thank you so much. That was great. I'll wait a few moments that audience can write a question. Just for curiosity, some of these objects that you make is probably look like the letter or digits. Does it change the reactions?
We were mainly planning that they didn't look like letters or objects. I can kind of go back if you want. Yeah, there we go. I guess you can kind of see some of them if you really look at them might. But no, we didn't look at any differences based on if they might look like letters or numbers. We were hoping they didn't.
But that's interesting to know because that like memory kind of thing may affect some way.
I did have a participant that strategy was to sort of pick what the different objects looked like, and he would talk out loud too, which was difficult with the eye tracker.
If no one has a question, I have a question.
Sure.
Would you say, as I understood it, people change this curvature is because like they're like, oh wait, this is the wrong thing I'm looking at. I'm gonna change my so does that insinuate that people are thinking about the object before they even saccade? So yeah.
Yeah, so I guess for our study, they had to stare, actually this panel that's highlighted here, they had to stare at the cross and use their peripheral vision to figure out which one was the target. And we only included correct trials for this study, like for this analysis at least. So I guess they would have seen in their peripheral vision that the target is the one that they wanted to look at as they were deciding to plan for the saccade. And so that's why we see with the longer reaction times when they had more time to plan and more time to decide which object was the correct one, that the saccade curves differently because they're able to, like, the distractor doesn't have as much of an effect on the saccade curvature.
Oh, I see. So you wouldn't say that they were doing any kind of perception while doing the saccade? Because, you know, there's the whole saccadic inhibition.
Yeah. I think maybe sort of unconsciously, yeah. I know when I was doing it myself, it goes really quickly, and I guess you end up seeing these effects even though you're sort of unconsciously deciding and you're just like, I'm gonna look at that one.
Okay.
Or at least it feels like it's unconscious.
Can I ask one more? Is it?
Sure, yeah, if nobody else has questions, sure.
Yeah, so the distance is the same, but you're saying that there's variance to the reaction time for the same distance?
Yeah, so it's the reaction time was more the time the participant just took to stare at the cross.
Right.
So as soon as they started moving their eyes, that was the end of the reaction time period. So it was just variance in participants' like trials, yeah.
But so the speed is the same for all the saccades because they're all because of the same distance. I would assume like the speed distribution is probably really tight.
That makes sense. I actually haven't looked at speed, but I probably should.
Okay. There's like all this like old literature like showing the correlation between saccade size and eye speed, and it's like really it's kind of a tight correlation. I'm just curious if you see that.
Yeah, thanks for the suggestion.
Yeah, and the trajectory are different when you have a further object, or the same almost?
Pardon?
The trajectory of eye movements, are they changing when you look at the further objects, or?
So both objects were equidistant to the target. We kept them at the same distance every trial. They were just different distances from each other.
Oh, but overall distance is fixed here.
Yeah. So it was at a 7.5 degrees of visual angle was that circle that they were placed around.
Sorry, then I missed that one, that you changed probably that angle. Oh, so they are the angular distance. And
Yeah, so actually right here, so the target was placed somewhere around the circle, and then the distractor was relative to the target, 5 positions on either side away, up to 5 positions on either side.
And that was symmetric for left and right, right? The result.
Yeah, we kept the same amount of trials left and right, yeah. We just grouped them together for the analysis.
I've got a more basic question.
Yeah.
Sorry. No, I mean,
yeah.
If other people have better questions, they should ask theirs.
Oh,
but...
yeah. There is not any question. Sorry, I have to clean up the last question, but I don't see new question coming. Yeah, go ahead if you want to ask.
So is so I'm assuming that if you only use one target, people move in a straight line to the target. There's no curvature in like a typical saccade from the central fixation to the target.
Yeah, I think that there's, sorry, were you done?
Oh, and then I had my follow-up to that is that if there are like 2 objects and there's like a target and a distractor, is the idea just that they make some like vector sum eye movement of like the attraction to the target and the other one, as opposed to like they like normally would go in a straight line to one and then maybe go to the other one next? It's interesting that like there's some like sort of summation of attractive forces from the 2 different objects that are there. That's what I'm confused about or curious about.
Yeah, so I think the idea is that, yeah, when there's only one object on the screen, it's relatively straight. There is sort of like a underlying curvature to a saccade, which is why we would normalize our data. But when there are the multiple objects, we do get this curvature. Yeah, sort of like you said, there's an averaging of the vector, like saccades to both, and you sort of average the vectors. And that's why we get that initial angle that's outwards, and then the curvature to sort of pull you back in to go to the correct object. But then you see differences in the direction based on how long you take, for example, which is what we were mainly looking at. I hope that answers.
And does it change over time? Like, do you have an adaptation here?
Pardon?
Does it change over time? Do you have like adaptation for this curve over time, like the subject are doing the experiment?
Oh, like as they do the experiment, does their curve? I didn't look into if later on in the experiment they had differences. That's a good point, though. Yeah, but I didn't look into that yet.
Okay, thank you so much. If there isn't any further question, let's thanks again all the speakers, and that was a great talk.